Imagine you're presenting quarterly earnings to your company's board. Your AI assistant confidently reports revenue grew by 17%. The executives celebrate, investors are optimistic, and major decisions get approved. Hours later, someone manually checks the spreadsheet. Revenue didn't grow, it actually fell by 2%. The AI wasn't hallucinating facts. It made one small reasoning mistake early in its calculation, and every step after that built on the wrong assumption. Today, you'll learn one of the most effective techniques for preventing exactly this kind of failure: self-consistency. Prompting, the method production AI systems use to make reasoning dramatically more reliable. But fragility isn't just about million-dollar mistakes. It happens in the simplest riddles, too. Take the famous "farmer had 15 sheep, all but 8 died" puzzle. A standard chain of thought model often gets tricked into answering 7. A single flawed reasoning step that looks confidently correct. That's the kind of mistake self-consistency was built to eliminate. By the end of this video, you'll own 3 new skills. Cold. You'll be able to explain how multiple reasoning chains vote and why that erases single-path mistakes. You'll write a working Python loop that calls an LLM 5 times and picks the majority answer. And you'll know when to reach for universal self-consistency on open-ended tasks where voting doesn't apply. Let's rewind. Standard chain of thought works like this. You get one reasoning path, one chain of logic. And because the model uses greedy decoding, it picks the most likely next token at every step. That makes it fast, but fragile. If even one early step goes off the rails, the entire downstream answer is toast. The riddle we're about to show you proves exactly that. Watch what happens when a standard CoT model tackles the farmer-sheep riddle. A farmer had 15 sheep. All but 8 died. How many left? The model confidently answers 7, reasoning 15 minus 8 equals 7, misreading all but. That's greedy decoding in action. Checkpoint: single path fragility. Checkpoint: CoT weakness. The fix came from Wang and colleagues in 2022. Instead of one reasoning chain, you generate multiple diverse chains and pick the answer that shows up most often. Think of it as putting the LLM inside a voting jury. Each juror walks a slightly different logical path, and the majority verdict carries the day. Complex problems usually have several valid ways to arrive at the same correct answer, and random errors tend to cancel out when you sample enough paths. Here's the machinery. You take the same chain of thought prompt, but run it 5 times with a non-zero temperature, say 0.7. Each run produces a slightly different reasoning trace and maybe a different answer. Then you let the 5 answers vote. The one that appears most often is the final output. This simple mechanism erases the luck factor of a single greedy decode. Let's make this concrete with the classic age problem. Run the prompt 5 times. 4 out of 5 paths correctly realize the sister is always 3 years younger and subtract accordingly. One path, maybe a careless hallucination, divides 70 by 2 and gives 35. But the math is brutal. 4 votes to 1. The majority correctly lands on 67. Self-consistency turned a potential flub into a sure answer. No single AI is infallible, but in a crowd, the truth tends to repeat. Individual paths may hallucinate a number or drop a sign, but the pattern of correct reasoning usually shows up again and again. Self-consistency doesn't make each chain smarter. It just smooths out the random noise. It's like asking 5 colleagues the same question and taking the answer they all agree on. You stop betting the farm on one shaky explanation. Time for a quick checkpoint. If self-consistency spits out 5 answers, 8, 8, 7, 8, and 8, what does the majority vote return? Got it? The answer is 8 because it appears in 4 out of 5 chains. The lone 7 gets overruled. That's exactly how self-consistency filters out one-off errors. Self-consistency shines when correctness is non-negotiable and the reasoning has multiple valid paths. Arithmetic reasoning, common-sense riddles, logic puzzles, and multi-step calculations all benefit because the risk of a single stray thought is high. But don't reach for it on creative writing or open-ended generation where several outputs can be equally right. Voting breaks down when there's no single correct answer. Those categories are where universal self-consistency steps in. Nothing comes for free. Self-consistency asks the model to solve the same problem multiple times, so your API cost and latency increase almost linearly with the number of reasoning paths you generate. But in production, reliability is often far more valuable than saving a few cents. If you're generating financial reports, medical recommendations, security analyses, or legal summaries, one incorrect answer can cost far more than 5 additional API calls. Great AI engineers don't optimize for the cheapest answer. They optimize for the most trustworthy one. You can implement self-consistency in about 10 lines of Python. Loop 5 times, call your LLM API with temperature set to 0.7 to get diverse reasoning chains. Extract the final numeric answer from each response, and then use Python's counter to find the most frequent result. The highlighted lines are the key. Temperature above 0 creates variety, and the counter gives you the consensus. The whole pattern is copy-paste ready. You can adapt it to any problem by swapping in your prompt and answer extraction logic. One practical checkpoint. What's the single parameter you must crank up to get diverse reasoning chains? It's temperature. Without a non-zero temperature, the model just repeats the same greedy path, and self-consistency collapses back into ordinary CoT. Set it around 0.7, and you get the variety you need for the vote to work. Here's where it gets counterintuitive. A product manager pings you. Give me the most concise summary of this 50-page technical report. I need it in 5 minutes. You run the prompt 3 times. One summary is 200 words, the next is 350, the third is 150. Which one do you send? Self-consistency can't vote here. There's no single correct answer to majority vote on. But a variant called universal self-consistency can still save you by using the LLM itself as a judge to pick the output that best matches a criterion like most concise. Self-consistency isn't just a math trick. It's a general reliability tool for any high-stakes language task. Universal self-consistency generalizes the voting idea. You still generate multiple diverse outputs, say 3 summaries or 3 code solutions, but instead of looking for a numbers majority, you feed them all into a second judge prompt. That prompt asks the LLM to rank or select the best one according to a criterion you define: most concise, most readable, most secure. The judge is just the LLM acting as a discriminator. This bypasses the requirement for a single correct answer and makes self-consistency useful on open-ended tasks. Here's what the code looks like. First, you call the LLM 3 times with a high temperature, say 0.8, to get 3 varied summaries. Then you wrap them in a judge prompt that explicitly asks, which one is the most concise? Return only A, B, or C. You run the judge with temperature 0 because you want a deterministic decision. The LLM picks summary C and you send that to your product manager. Notice the judge prompt doesn't need to know the right answer. It just needs a clear criterion. That's the core insight of USC. Here's why engineers spend time learning techniques like self-consistency. Companies aren't hiring people who simply know how to write prompts. They're hiring engineers who can build AI systems that consistently produce dependable results. Whether you're creating customer support assistants, software development co-pilots, security automation, or enterprise search, improving reasoning reliability directly improves product quality. Knowing how and when to apply techniques like self-consistency separates someone experimenting with AI from someone designing production AI systems. Let's make this practical. Imagine an AI assistant helping an IT administrator troubleshoot a production outage. One reasoning path concludes the DNS server is down. Another blames a firewall rule. A third correctly identifies an expired certificate. Acting on the wrong diagnosis could leave hundreds of employees unable to work. By generating multiple reasoning paths and selecting the most consistent conclusion, or escalating when there's disagreement, the assistant becomes significantly more reliable. That's why production AI systems increasingly combine reasoning techniques with validation instead of trusting the first answer they receive. The biggest difference between a beginner building AI demos and an engineer building enterprise AI isn't prompt length or fancy wording. It's reliability. Real companies care about systems that produce accurate answers day after day, not impressive one-time demonstrations. Self-consistency is one of the simplest ways to improve that reliability because it reduces the chance that a single reasoning mistake reaches your users. That's exactly the mindset companies expect from engineers building production AI. Before we move on, let's see where self-consistency fits in your growing toolkit. Across this masterclass, you've already learned zero-shot, one-shot, and few-shot prompting. Then chain of thought for step-by-step reasoning, tree of thoughts for exploring multiple paths, and react for agent-like action loops. Today's technique, self-consistency, adds a voting layer on top of CoT to catch mistakes. And there are 3 more techniques coming soon: reflection, critique, and revise, and debate prompting. They'll level you up even further. Reflection. Prompting works like a self-critic. The model first generates an answer, then you explicitly ask it to critique its own output, pointing out flaws, assumptions, or missing steps, and finally revise. This loop is fantastic for code review, essay polishing, or any task where improving upon a first draft increases quality. We'll dive deeper into reflection in a later video. Critique and revise builds on reflection by turning it into a loop. Generate, spot issues, fix them, check quality, and repeat. Here's where self-consistency fits perfectly. You first use the voting method to get a robust answer, then run critique and revise to polish it even further. The combination drastically cuts down on subtle errors that even a majority vote might miss. Let's lock that in. Reflection has one model reviewing itself. Critique and revise loops that self-review. But debate prompting involves multiple models arguing against each other. All 3 are ways to get more reliable outputs, and the series will give you the full toolkit soon. Self-consistency is powerful but not free. Running 5 reasoning chains means 5 times the compute cost, something to watch if you're calling an API thousands of times. The technique also still relies on those few-shot examples being solid. Feed it garbage demonstrations and all those diverse paths will just be diverse garbage. Finally, it can't fix creative writing where correctness isn't clear. Voting doesn't work when multiple answers are valid. That's where universal self-consistency and the upcoming debate prompting come in. One practical objection to self-consistency is the manual work of handcrafting those few-shot COT examples. This is where Auto-CoT comes in. The technique, proposed in research accompanying self-consistency, automatically generates diverse reasoning demonstrations, so you don't have to manually write 5 different step-by-step examples every time. It makes building a self-consistency pipeline at scale far more practical. Now let's zoom out and look at how this works inside a real AI application. A user submits a question. Instead of making one LLM call, your application sends the same prompt to multiple reasoning chains in parallel using controlled randomness. Each response returns its own answer. A lightweight aggregation service then compares the results and selects the majority answer, or forwards the outputs to an LLM judge if you're using universal self-consistency. Only after that verification step does the application return the final response to the user. This architecture keeps the voting logic outside the model, avoids context window limitations, scales efficiently across parallel requests, and is the pattern you'll see in many production AI systems. Final checkpoint before we wrap up. When you build a self-consistency loop, the number of candidate chains is limited by the context window if you're doing in-context voting. That's why many production implementations aggregate externally, using simple majority voting outside the LLM to keep costs down and avoid hitting token limits. Here's probably the biggest misconception about self-consistency. Many beginners think increasing the temperature automatically improves reasoning. It doesn't. Higher temperature only creates more diverse reasoning paths. If your original prompt is vague or poorly designed, you'll simply generate 5 different wrong answers instead of 1. Self-consistency improves reliability only when each reasoning path has a reasonable chance of reaching the correct conclusion. Always start with a strong prompt, clear instructions, and enough context. Voting can reduce random mistakes, but it can't rescue poor prompt design. When not to use self-consistency. Creative tasks. If you're writing poetry or stories, multiple perfect answers exist. Majority voting crushes style and picks the blandest common denominator. Latency-critical apps. A real-time chatbot that votes 5 times per query will feel sluggish. You're trading user experience for a reliability gain they'll never notice. Weak base prompts. If your chain of thought examples are sloppy, self-consistency just puts a committee of idiots in charge. Fix the underlying reasoning first. Let's lock in your new toolkit with the 3 big takeaways from this video. Takeaway 1. Majority voting fixes single-path reasoning mistakes. By sampling multiple chains and picking the most common answer, you catch the random slips that would derail a single chain. 2. A production self-consistency loop is surprisingly simple. A Python loop that calls your LLM with varied temperature, collects the answers, and counts the winner, gives you this reliability in code. 3. Know which version to reach for. Standard self-consistency works best when there's a clear right answer: math, logic, classification. Universal self-consistency shines when you need the best open-ended output, like a summary or email draft, by having the model judge its own outputs. With these 3 skills, you're no longer hoping your AI gets it right. You're building a system that verifies it. Homework time. First, copy the farmer-sheep riddle into your LLM of choice. Run it 5 times with a chain of thought prompt and temperature 0.7. And count how many times you get 8. Second, do the same with the age riddle, just 5 runs and a tally. If you want to go further, try USC. Feed a 3-paragraph news article into 3 completions, then write a judge prompt that asks the model to select the most concise summary. Use our Python snippet from earlier as the template. It's just a loop and a counter. You've now built a reasoning engine that's far less likely to chase a hallucination off a cliff. Next time, we'll give that engine a proper hull. Structured outputs. Picture this. You get a rock-solid answer from self-consistency, but it's buried in a free text paragraph. Half the value is lost. In the next installment, XML versus JSON prompts. Which structure gets you hired? You'll learn how to force the output into a clean, parsable format so your pipeline can actually use it. We'll cover when JSON wins, when XML still matters, and how to craft prompts that never break your data flow. It's the difference between a demo and a production-ready feature. See you there. Checkpoint time. What is the #1 beginner mistake with self-consistency, and why does it backfire? Imagine asking 5 experienced engineers to independently review the same architecture diagram. They won't all explain it the same way, but if 4 identify the same configuration issue, you'd probably trust their collective judgment more than a single opinion. Self-consistency applies the same principle to AI reasoning. Instead of betting everything on one chain of thought, you let multiple independent reasoning paths compete before selecting the answer. That's a simple idea, but it's one of the biggest reasons modern AI systems are becoming more dependable. Congratulations! You've just learned one of the most important reliability techniques used in modern prompt engineering. If you're following this masterclass from the beginning, you're building a toolkit that mirrors how production AI systems are designed, not just how demos are created. If you found this lesson valuable, subscribe and continue with the next episode, where we'll explore structured outputs using JSON and XML prompts. Together, these techniques transform isolated prompts into dependable AI applications. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.